Enzymes are proteins or ribosomes that act like catalysts. They usually contain one or more active sites where reactions with very specific substrates take place. The German biochemist Leonor Michaelis and the Canadian biochemist Maud Menten proposed a mechanism to explain the dependence of the initial rate of enzyme-catalyzed reactions on the concentration of reagents. This mechanism involves a very specific substrate and an enzyme forming an equilibrium with the combined substrate-enzyme complex. This complex then reacts to form the product and regenerate the enzyme to catalyze another substrate. The Michaelis-Menten mechanism can be written quantitatively as a specific substrate and an enzyme form an equilibrium with a combined substrate-enzyme complex, with rate constants for the forward and reverse reactions Kf and Kr respectively. This complex then reacts to form the product and regenerate the enzyme with a rate constant of Kcat. It can be assumed that the concentration of the substrate-enzyme complex quickly reaches a constant value, meaning the steady-state approximation holds, and under the case that the initial concentration of the enzyme is much less than the initial concentration of the substrate. Therefore, the rate of formation of the products is equal to the rate constant Kcat times the initial concentration of the substrate times the initial concentration of the enzyme all over the initial concentration of the substrate plus the composite constant. This is the Michaelis-Menten rate law, where in this case we will call the composite constant the Michaelis constant, and that this matches the simple catalyzed reaction scheme that we examined before, where we would use a Lineweaver-Burk plot to analyze the data. As was indicated before, Vmax is the maximum rate that's attainable. If the initial concentration of the enzyme is known, then the maximum rate Vmax can be used to determine the turnover number, or Kcat. Recall that Kcat is the rate constant governing the reaction between the substrate-enzyme complex and the product. So the turnover number represents the number of substrate molecules that are converted to product per unit time when the enzyme is fully saturated with substrate. Recall that the Michaelis constant, Km, is a ratio of the three rate constants involved in this mechanism. It also represents the substrate concentration at which half the enzyme active sites are filled by substrate molecules. Another way to put this is Km is equal to the initial concentration of S when the reaction is operating at half the maximum rate. To show this, we start with the rate law expression and set the rate to be half the maximum rate. We can then solve for the Michaelis constant and find that it is equal to the initial concentration of the substrate. The Michaelis constant varies greatly from enzyme to enzyme, and within the same enzyme for different substrates. It also depends on temperature, pH, ionic strength, and other reaction conditions. Let's now look at an example where we will have a reaction that is governed by Michaelis-Menten kinetics that, in this case, is catalyzed by an enzyme called carbonic anhydrase, and that based on some initial data, which is what we have written down in this table over here, what we're going to do is we're going to determine the Michaelis constant Km and the rate constant Kcat for this enzyme at this temperature, where the temperature is just above the freezing point of water at 273.65 Kelvin, and we're given an initial concentration of the enzyme being 2.3 nanomolar. The reaction under study in this case is one that involves the reversible hydration of carbon dioxide into bicarbonate, which is written down right here. And it was something that was originally studied by DeVoe and Kistinkowski, which they published in the Journal of the American Chemical Society back in 1961. And this process is one that happens inside our bodies, and it's one of the ways that carbon dioxide is transported through the bloodstream and from our cells to our lungs to be exhaled. So because the analysis, in this case for the Michaelis-Menten mechanism, that we're going to be using a Lineweaver-Burk plot to analyze it, I've already taken the liberty to take the inverse of the rates and the inverse of the initial concentrations of the carbon dioxide, which was taken from the table that I initially pointed out up here. And what I've done is that I've plotted in this figure, and I've fit the four data points to a line, where in this case we have a slope that's equal to 39.97, and we have a y-intercept that's equal to 4002. And so it's going to be based on these values that I'm going to be determining what is my maximum rate for this reaction, and based on the slope I'm going to be finding out what exactly is my Michaelis constant. So starting off with finding the maximum rate, which is again is the y-intercept here, or I can get it from the y-intercept, I'm going to use that to find my kcat, which is one of the parameters that the question asks. And that we know that the y-intercept is equal to the 1 over the maximum rate, which means that if I want to have something that describes the maximum rate pulled off from the plot, then that's equal to 1 over the y-intercept. And I know that from before, the maximum rate, well, that's equal to my rate constant kcat times the initial concentration of my enzyme. And so in this case, I'm going to substitute in for my maximum rate the inverse of the y-intercept, which in this case is going to be 1 over 4002, and that's equal to kcat times the initial concentration of the enzyme, which is given in the text of the problem, 2.3 times 10 to the minus 9, since I want to work in molar, or moles per liter, and not in nanomolar. And so when I simplify and I solve, then I get my rate constant kcat being equal to 1.1 times 10 to the 5 inverse seconds. And then to find my Michaelis constant, I'm going to use the slope of the line, because I know that that's equal to the Michaelis constant divided by the maximum rate. And so what I'm going to do then is I'm just going to rearrange, and I'm going to have my Michaelis constant is equal to the slope found from the fit times the maximum rate. I can then substitute in for those numbers. The slope is 39.97, and my maximum rate was 1 over 4002. And so when I substitute, or when I solve for this, then what I get is 9.99 times 10 to the minus 3 molar. In this lecture, our objective was to quantify rate law expressions for enzyme-catalyzed reactions. Here is a summary of what we covered. A catalyst is a substance that is not consumed by a reaction and offers an alternative reaction pathway whose rate is faster than the original reaction. An enzyme is a protein or ribosome that acts like a catalyst on very specific substrates. Their initial reaction rate can be described using the Michaelis Menten rate law. And determining the turnover number, or kcat, and the Michaelis constant, km, can be achieved by fitting data using a Lineweaver-Burke plot.